In this video, I'll be teaching you the components and functions of an electrolytic cell, and also how to calculate voltage. Here is an example of a voltaic cell. We start with two beakers. In the first beaker, we have a copper 2 sulfate solution, and in the second beaker, we have a zinc sulfate solution. In the copper 2 sulfate beaker, we add copper metal, and in the zinc sulfate beaker, we add a piece of zinc metal. Next, we connect them with a wire, and lastly, we have a salt bridge. I will ignore the salt bridge for now, and I will explain about what the use of it is later on. Here is a closer look of what is actually happening. Copper 2 plus itself has a stronger pull of electrons compared to zinc, so it gradually pulls electrons away from the zinc. Zinc loses electrons and it travels through the wire to combine with the copper 2 plus, which will then get rid of the charge and just become part of the copper metal. It will then look something like this. Notice how an atom of zinc turned into an ion as it lost 2 electrons, and one of the copper ions turned into a copper atom by gaining 2 electrons. After some more time has passed, it will look something like this. As you can see, the copper is gaining electrons. This makes it a reduction reaction, and it will act as a cathode. On the other hand, zinc is losing electrons. This makes it an oxidation reaction, and it will act as an anode. So we initially started with something like this, and as more and more electrons from zinc transfer over to the copper 2 plus, it will look something like this. So for our reduction half reaction, we have this. Our zinc 2 plus half reaction will look something like this. We add both equations, and the electrons can cancel out each other, and we are left with this net ionic equation. But remember how it was initially filled with copper 2 and zinc sulfate? Well, the sulfate is still here. Our overall result is that the beaker with copper 2 sulfate is gradually becoming more negative, and the beaker containing zinc sulfate is gradually becoming more positive. If both sides gather too much charge, the voltaic cell will not run anymore. So this is where the salt bridge comes in. For our case, the salt bridge is composed of sodium chloride ions. On both ends of the salt bridges are pieces of cotton that restricts all sodium chloride ions from falling out. Because the left beaker is gradually becoming more negative, positive sodium ions begin to filter out of the salt bridge to balance out the negative charge. Negative chloride ions begin to filter out of the salt bridge to the right beaker to balance out the positive charge. Now what is the voltage of the wire? To calculate the voltage, we have this equation. We have E cell equals E cathode minus E anode. The circle beside the E means at standard temperature and pressure. We have this net ionic equation. The oxidation part and the reduction part are as follows. We then look at a charge with standard half reaction potentials. We find the voltage of E cathode over here, and E anode over here. We end up with this equation. The two negatives cancel out each other and we form a positive, and we end up with a voltage of 1.1 volts. Let's look at another example. Copper 2 plus and barium forms copper and barium 2 plus. Here are oxidation and reduction reactions. We find the half reaction for copper over here and the half reaction of barium over here. We end up with this equation, and the two negatives form a positive, and we get a voltage of 3.24 volts. That is it for this video. Thanks for watching.